Greetings, environmentalists. We're down to our last two lectures of the semester, so yay! We'll be learning about climate change, and I think we're going to shape your paradigm, your current views, hopefully, and your knowledge base about what climate change really is about. So what are our learning objectives for this lesson? First, we're going to compare and contrast anthropogenic, we'll learn about that word soon, and cosmic impacts of climate change. Both can cause climate change and both do cause climate change. We'll identify and explain how specific climate drivers impact climate change, and I'll be kind of explaining in detail how a driver is different from some of the other factors that we'll learn about, such as feedbacks. Recognize and explain how specific climate feedbacks impact climate change, and a feedback is one of the things we're very interested in terms of kind of controlling from our end is the human side for climate change. We're going to understand how the global energy budget impacts climate change and how adjustments in that budget can lead to either a climate warming or a climate cooling, and we do have both throughout geologic history. We're going to review a case study of previous climate change. So let's address the elephant in the room. So we need a disclaimer right up front. If there's not a single topic on the planet where the public, marketing efforts, media efforts, politicians have impacted people's, meaning the general public's view, it is this topic of climate change. Why is that? Why is climate change such a hot tamale? And I don't mean that in the sense of, oh, hot climate change or warming. Well, it's become associated, that means climate change, with stereotypes that are often not linked to any kind of actual data for science. My hope is by the end of these two lectures that you have some foundation to put you in a place to have an intelligent conversation, a crucial conversation about one of the most important things that we'll face as humans in our lifetime. It affects everything from our drinking water to our food supplies and everything in between. It's really about survival. The goal of this lecture is for you to determine if climate change is real or if it's a myth. You get to make the decision. But at the end of the day, I think you're going to find out that it's something you need to be concerned about. Let's determine what climate change really is. First of all, let's define it. Climate represents the average pattern, keyword is average there, of weather over the long term, including temperature, pressure, precipitation, wind speed, cloudiness, and the other types of things that define weather. So understand it's the long-term weather. So it's average weather patterns, not just a week or a month or a year. We're looking at long-term, which is typically 30 years or more in human reference. The Earth's climate has warmed and cooled for millions of years, even billions of years. Probably our most significant ice age actually occurred back in the Precambrian, and it's called Snowball Earth. Temperature is critical to the climate story because it controls a couple of important things. First of all, temperature controls evaporation rates. These evaporation rates in turn drive the water cycle. Well, the water cycle is critically important to the climate change story. It controls cloud formation, another important climate story factor, and it increases and actually creates winds. Winds, along with ocean currents, drive our climate system around the world. They cannot be understated. So what's the energy budget? You're thinking a budget like dollars. Well, I want you to kind of think that way because it's the Earth's response to balancing its temperature based on how much energy it receives from the sun, absorbs at the Earth's surface, and then how much of that energy gets reflected back to space. So we need to think about that again for a minute. How much do we receive in? How much do we absorb? And then how much do we reflect back? Those three features are going to determine what the budget is. So long story made short, if I have all of the sunshine coming in, we're going to capture some of that heat here in the atmosphere. That's what greenhouse gases are. They're actually a good thing. You always hear negative stuff about greenhouse gases, and we want some, or else we would be a frigid planet. We'd be very cold, like Mars. Too much of a good thing will put us in the Venus situation when we don't want that, right? So there's a fine balance. So on a normal given period of geologic time, the Earth can regulate this in such a way that we have a balance between how much is coming in and a pretty equal amount going out, with some absorption here at the surface. Now, another thing to consider is that let's change the equation. Let's say we start having more gases that can obtain heat here. We'd have a global warming or a climate warming. Let's say that we're reflecting more sunlight than we're actually absorbing. Just the opposite would occur. We'd have a global cooling. So when you're thinking about these aspects, I want you to realize that you'll usually hear about the climate warming side of the story, but the climate cooling is just as important.
It's not always easy to keep track of my money and to be sure that the amount that I earn equals the amount that I spend. Balancing my budget gets tricky.
Today, we're going to find out how that money isn't the only thing that's tricky to balance in a budget. Atmospheric scientists worry about balancing Earth's radiation budget. We'll talk about that next on Real World. Everyone knows Earth gets its energy from the sun. Keeping track of all that energy is really important. NASA uses Ceres, a data collecting sensor on satellites that are part of the Earth observing system. Ceres measures the amount of energy the Earth receives and also the amount of energy it returns back into space. The name Ceres is an acronym. It stands for Clouds in the Earth's Radiant Energy System. It's also the name of the Roman goddess of agriculture. Ideally, the amount of energy coming to and leaving Earth should be the same, equal, giving us a balanced radiation budget. And that would mean Earth's surface is neither cooling nor warming from year to year. The energy coming from the sun is visible light, or shortwave radiation, and much of it never reaches the surface of the Earth. In fact, about 50% is actually reflected back into space or absorbed by our atmosphere and clouds. Do the math. That leaves only about 50% of the energy to be absorbed by land and the oceans. Darker surfaces tend to absorb more energy, so places where there are oceans and rainforests absorb a lot of the sun's radiation, around 75% for the oceans and 85% for the rainforests. But lighter areas, like deserts and polar regions, are reflective, and thus absorb smaller portions of the sun's energy. Around 65% for deserts, and 15 to 60% for the polar regions. The energy that is absorbed by Earth's surface is converted to heat or long-wave energy, and then sent back out towards space. But not all of that energy makes it back to space. Some of it gets trapped by the atmosphere, creating the greenhouse effect, and it makes Earth warmer than it would be without the atmosphere.
The Ceres instrument carefully measures the total energy leaving the Earth.
Data gathered by Ceres sensors suggests Earth may be warming up even more, due to changes in the atmosphere.
We're looking at how clouds interact with sunlight in the Earth system and with heat.
Lynn Chambers is a member of NASA's Ceres science team.
We already have pretty good indications that there is an imbalance in the energy in versus the energy out.
This is caused by the increase of greenhouse gases, which include carbon dioxide, methane, and other trace gases.
The scientific information is pretty compelling that if you add carbon dioxide to the atmosphere, you expect to see a warming, and we do see indications of that warming.
You may have heard talk about a carbon footprint. What's a carbon footprint? That's simply the amount of greenhouse gases created due to human activity, like driving a car, and how those gases affect our atmosphere. For example, the average car adds around 5,000 kilograms of greenhouse gases to the atmosphere each year. That's 5 metric tons. Our carbon footprints are causing the polar caps to melt, and that's leading to an increase in temperatures. Remember? dark surfaces like the ocean absorb heat and energy, while the lighter surfaces like the polar ice caps actually reflect it. Less ice, more ocean, more heat absorbed.
So, when you think about your own budget, try to think about Earth's radiation budget, and try to keep both balanced.
You can find out more about the series program by going to www.nasa.gov and searching for school. That's NASA's Students Cloud Observation Online Project.
That was an excellent overview of some of the albedo, which is the color of the Earth. We'll get to that term here in a little bit, but he addressed it in the video, saying that dark surfaces absorb heat, lighter surfaces like land that's deserts, sands, things that are white like the polar caps will reflect sunlight. That's going to shift us from having a warming trend to a cooling trend. So let's look at the impact of greenhouse gases in the story of climate change. The Earth's atmosphere keeps much of the sun's energy from escaping into space. This process helps the planet be warm enough for life like you and me to exist. So if we had this imbalance regularly, we would have extinction, and we might have a point where we can have no life if it was too cold or too hot. Greenhouse gases absorb and hold some of the heat, reducing the amount of radiation that's reflected back into space. So without greenhouse gases, you and I would not be living comfortably. This is stuff you need to know for your test. 50% of the sun's heat reaches the Earth's surface, or at least this is a balanced budget that he was talking about a minute ago. 30% of the sun's energy reaches the Earth's surface and is reflected back into space. 20% of the sun's energy is absorbed by greenhouse gases in the atmosphere. So let's change some equations here. Let's say that let's change the middle factor, the 30% of the sun's energy reaching the Earth is reflected back to space. Let's say that 50% is reflected and we have a much less number for the greenhouse gases and even the sun, that our amount of radiation that reaches the Earth's surface. We would have a cooling. So let's actually change that aspect and say, all right, let's raise the last category of 20% of greenhouse gases and increase it to 30%. So at that point, in order to reach 100% of the whole amount of radiation, the budget's got to, kind of stay at least at 100%, then you're going to have a warming. So this fancy chart right here is something that you'll be working on in your lab to interpret, hey, what's happening here? What's going on? Why is this material coming in, the sunlight coming in, where are we losing it? And why are these numbers written the way they are? It's actually kilowatts per square meter. And so we look at kilowatts as the key factor of how we describe energy that comes in and energy that leaves the Earth. Long wave radiation is different than short wave radiation because short wave radiation coming from the sun can pass through at a much faster rate, and certain meaning elements, specifically like when you're looking at nitrogen, just pass right through. Well, if you know about the Earth's atmosphere, nitrogen makes up a bulk of what we've got. It's the long wave radiation that we're the most concerned about because heat is absorbed. It can travel slower through the atmosphere, and then if we have these specific concentrations of greenhouse gases present that absorb long wave radiation, then we have a potential for warming. What are some of those look like? Water and water vapor. Certainly carbon dioxide, and I might point out that out everything that we're going to look at in terms of air quality stuff that's regulated, it's carbon dioxide that's not. That may surprise you, but there's a whole nother semester to learn about that if you want to talk in depth. Nitrous oxide is known as NOx gases. They absorb heat because they absorb long wave radiation. Then of course we got methane, which holds substantially more heat than carbon dioxide per molecule. And then last but not least, we have sulfur dioxide, and that is going to be the stuff that we know as SO2. Regardless of which one of these things they are, greenhouse gases, if we have too much in the atmosphere, It's kind of like eating a pumpkin pie at Thanksgiving. If I have an entire pie and I eat it all on the same day, and I have really chomped down food during my Thanksgiving celebrations, I've way exceeded my caloric intake balance for the day. Remember, I just ate a whole like 14-inch pumpkin pie or pecan pie. I'm probably going to see the scales tip in the direction of weight gain, right? Unless you have like a superhero metabolism. But assuming you're an average metabolism person, you would gain weight. Now let's look at this equation a little differently. Let's say that you ate that pie one slice at a time over a month or two, and you're exercising regularly, so your caloric intake is balanced. You wouldn't gain weight. The problem with our situation with the climate right now is that the atmosphere cannot handle the amount of pumpkin pie it gets. So let's change the term pumpkin pie with greenhouse gases. In other words, it can't burn it up, absorb it fast enough. So it's accumulating it like that. And so as it accumulates it, we're getting warmer and warmer with our climate. What's the overall effect or impact? When more greenhouse gases get added to the atmosphere, this decreases the amount of long-wave radiation being emitted from the Earth back to space because it's absorbed. This pushes the Earth out of its normal energy balance. When this happens, it's because more heat comes in than is released. If we have this type of shift, we're going to have a warming trend. The opposite would be true that if our budget gets out of whack the other direction, where we have more of the radiation being released back into space. If that were to happen, then we would have the other extreme, the polar extreme, literally. We would have a climate cooling. So how does this all relate? We have a compensation effect. So you're looking at some limestone over here. The Earth's temperature will increase until the amount of radiation leaving matches the amount of radiation coming into the atmosphere. How does this happen on Earth? Well, we got this nifty thing on Earth called the ocean. And this ocean is notorious for grabbing things like carbon, sucking it out of the atmosphere, and making rocks out of it. Is that not like one of the most ingenious things you've ever heard? So our ocean's in the business of trying to balance the budget for us. So if we have too high a percentage of carbon dioxide existing in the atmosphere, the Earth's ocean absorbs it and stores it in carbon-rich rocks like limestone. All right, so think with me strategically for a moment. If I've got a lot of limestone and it's at the surface, and we start to take that limestone, we start to crush it, we start to make concrete out of it, all the things that we use limestone for, am I not releasing that CO2 back into the atmosphere? That's what I'm wanting you to think about. Another thing to consider, if the ocean warms too much, the acidity in the ocean will rise. Well, limestone's very susceptible to karsting. Karsting is where it gets holes in it from acidic groundwater or surface water. So if the ocean gets acidic, we're going to be breaking down that limestone, and would we not have more carbon dioxide being released? I think you can see where I'm going with this. It becomes a very big dilemma. What are the two factors that impact the energy budget? The sun's output of solar radiation and the distance and orientation of the sun and the Earth. Even a small change in the Earth's energy balance can occur if one of these two things happen. So let's look at climate drivers. A climate driver is any factor that affects the movement of energy through our atmosphere, but it's not impacted by change. So I'm going to go back to my pumpkin pie for a minute. That pumpkin pie was not impacted by the fact that it was made. In other words, it was just there. I was looking at that pumpkin pie. I was spying on it, thinking that was going to be mine. But that pumpkin pie was not affected by my eyes until I decided to eat it, right? So it's kind of like a climate driver. Climate drivers themselves are not affected by climate change. However, they do cause climate change. So this means that the climate drivers impact climate conditions, but they themselves are not impacted by the change in climate conditions. So we'll be looking at a handful. We'll look at solar output, the tilt of the Earth, the path of the Earth's orbit around the Sun, continental drift and plate tectonics. We'll look at volcanic eruptions, meteor strikes, and other massive atmospheric disturbance factors. So number one, these drivers you need to know for your test. Solar output. The Sun consistently emits a fairly predictable and steady amount of energy. It's been doing that for billions of years. However, the Sun sometimes steadily increases its output or it decreases its output of energy. This can happen because of things like sunspots or solar flares or solar prominences. These fluctuations result in either a warming or a cooling effect, depending on if it's emitting more or less. Obviously, it's emitting more energy, you have a warming. If it's emitting less, you have a cooling effect. So when we think about one of these, the first item on the agenda is a sunspot. These are dark patches on the sun, and the surrounding margins of a sunspot are brighter and hotter in temperature. So it seems completely backwards. You're like, oh, it's going to make it less temperature. It's actually warmer when we have periods of more sunspots, and it's cooler when we have less sunspots. Make sure you get that right. So the more sunspots we have, the more energy is being released around those hot areas. And then the fewer sunspots that we have, the cooler the climate. Obliquity is the second item on the agenda. That's the tilt of the Earth, its axis. That's what obliquity stands for. This is the change in the tilt of the Earth's axis, and it directly affects the magnitude of seasonal change that we have. At a higher degree of tilt, the seasons are more extreme. In other words, the North Pole in particular will have a more extreme winter than they would normally. And at a lower degree of tilt, they are milder, so you would have a more mild winter in those areas. The current axial tilt is approximately at 23.5 degrees. So as it fluctuates about 1.5 degrees or so, that can make a big difference on how much radiation the North Pole gets. Number 3 of the drivers, the path of the Earth's orbit around the Sun, eccentricity. To be expected, a planet's surface temperature adjusts as it varies its proximity from its own star. Every star possesses a surrounding area referred to as the habitable zone, or the Goldilocks zone if you're looking for life. This is the area where life is believed to have the greatest odds of developing. Earth is in the Goldilocks zone or the habitable zone. Could we have had life on Mars? Maybe. Could we have life on other planets or moons? Maybe. And so the key is, where would you most likely have that life because of certain ingredients? Orbital eccentricity, the shape of the Earth's orbit changes from being elliptical to highly eccentric, or eccentricity, which is where it's extremely egg-like. So if you have a very low eccentricity, that's circular, in a cycle from going from circular to here, you can have substantial big differences in weather and in climate. When the orbit is highly elliptical, the amount of insolation received at perihelion when it's closest to the Sun could be in the order of 20 to 30% greater than aphelion, resulting in a very warmer climate. The opposite happens when you have a very circular type system. You're going to have milder winters, but you're going to have cooler summers. So if you developed a chance to have glaciers forming, let's say your axis tilt is you're getting less solar radiation at the poles, you'll have an ice age. So each one of these represents a change in climate. Continuing our eccentricity, the habitable zone, also referred to as the Goldilocks zone, is where the temperature is not too hot, not too cold, just right, because the water molecules are able to undergo each state of matter change, which is a solid, ice, liquid water, and water vapor, in order to fully produce a hydrologic cycle. That's what Earth is. Most often, the primary types of celestial bodies that sought out by scientists are super Earth-sized planets that reside within alien stars' respectable habitable zones. Scientists regularly use both radio and optical space telescopes to pan the heavens, searching for blinking quote-unquote stars, and then deducing said stars' variances in gravity to indicate the locations of where these planets are relative to their alien stars. So we're in the business of looking for where would the Goldilocks planets be. The fourth factor is continental drift and plate tectonics. Tectonics change plate positions. So that's all driven by hotspots under the surface. So as tectonic plates change their position around the planet caused by crustal heating, sometimes the planets attach themselves to each other. So these plates move attached land masses to new locations. When this occurs, we might expect to experience extreme warm or cold temperatures based on the latitude in which those particular plates have ended up residing. This has become a repetitive theme over geologic history. We can definitively say as scientists that there's been two supercontinents, one back in the Precambrian, and that was almost about 1 billion years ago, called Rodinia, and then one that came together at the beginning of the Permian period in the Paleozoic, known as Pangaea. So about 150 million years ago, Antarctica, hard to believe, but this was a massive warm swamp that was home to many different dinosaurs. You're going, no way, but yes way. Cryolophosaurus is an example of that. Here he is over here to the left. Sometimes he's called Elvisaurus. So the Antarctic tectonic plate drifted to its current location in the South Pole as Pangaea began to split apart, and especially during the Mesozoic. 5. Volcanic eruptions and meteor impacts. Both volcanic eruptions and meteor impacts thrust dust and debris into the atmosphere. These events have a short but important, powerful impact in reducing the sun's radiation from reaching the Earth's surface where most animals and plants live. I will tell you in these cases, it's short-lived. In other words, the ash, the particulate matter, it doesn't stay long-lived. It won't last for centuries. It'll last for a couple of years. In the most extreme situations, it's been proven that there were a number of extended times in geologic record when the Earth was either completely or mostly iced over with temperatures near or below freezing, even along the equator. There are two perceptions of this. One is snowball Earth, when the planet freezes completely from the poles to the equator, and then there's the slush ball Earth, when the planet is frozen nearer at the poles and middle latitudes, but leaves mostly an open ocean and exposed land for some plants and animals along the middle latitudes to the equator. So there are many scientists that think we didn't have a slush ball Earth. There are others that think we did. So there's some that think we had a snowball Earth during the Precambrian. So when you look at snowball Earth versus slush ball Earth, it's hard to say. There's proof that leans in both directions, but we don't have a firm, solid case to tell you it was one or the other. But we do have a case for this. We know there were glaciers during this time. So there definitely were ice packs. So let's talk about climate feedbacks. A climate feedback is any change or changes on the Earth which amplify or dampen climate change. Let's go back to my pumpkin pie. I ate it all at once, it's going to amplify my weight. If I eat it slowly or have none of it at all, and I'm exercising regularly in a balanced diet, I'm probably going to dampen or lose weight. So think about feedbacks like gaining and losing weight. Climate feedbacks are caused by changes in the Earth's albedo, which is the Earth's color at the surface, and are variances in the concentration of greenhouse gases in the atmosphere. So the darker the surface, the more heat is absorbed. The lighter the surface, more heat is reflected. So darker albedo occurs when the Earth has a higher percentage of darker colored surfaces. What do these include? Rainforest and oceans. So think about this. As we start to clear our rainforest, it's more than just about animals. It's also about the entire climate system, right? When you're looking at how important that heat can be to survival of maintaining a balanced climate. So if we're starting to take a whole bunch of ocean water out for desalinization, it would take a lot of ocean water, but we could do it. You could see that there could be a detrimental impact to climate. A lighter albedo occurs when the Earth has a higher percentage of lighter colored surfaces. What do these include? Deserts and glaciers. Lots of pavement that's light in color can do the same thing. This will cause a cooler climate. So what is radiative forcing? This is the net change in energy balance of the Earth's climate system. It's the difference between energy arriving from the sun and escaping back into space. Energy is described in watts per square meter, as we mentioned earlier, and the greater the overall imbalance of heat, the higher or warmer the watts per square meter will be. So that means you'll have a warmer climate. The lower the watts per square meter, the cooler the climate will be. So if you see the 0 mark right here, everything above 0 is a positive watts per square meter. Sometimes you can actually have a negative watts per square meter. The whole premise is you want to have a balance to make it an even climate, a balanced climate. But you can see, for example, our biggest problem right here is carbon dioxide. Then you look at methane, NOx gases, halocarbons, which are some trace gases that we create. And then you can look at some of the negative forcing items over here. So I want you to notice also, let's take the bar over here for CO2 and come over here and know what net anthropogenic contributions are. Anthropogenic refers to human-caused pollution or human-caused stuff. So if most of our positive radiative forcing is coming from human-caused things, that's something that maybe we can look at. So let's take a look at radiative forcing and aerosol particles. When high volumes of black carbon-containing particles enter the atmosphere, the dark particles absorb radiation just like dark surfaces do. This causes the climate to warm. When high volumes of lighter concentration colored particulate matter, such as volcanic ash, get into the atmosphere, this actually causes the reflection of heat back up into outer space, and this will cause the climate to cool down. This is one reason that businesses and industry are regulated for this kind of thing right here. Emissions that create black sooty material that can absorb heat. So changes in radiative forcing over time. Volcanic aerosols only last a few years, as I mentioned earlier, but greenhouse aerosols last decades. The forcing is different in the ocean, however. Like I said, the ocean is like our magic thing that works for us to balance the climate budget. And here's why. It's because water has an unusually high heat capacity. In other words, it can absorb a lot of heat. This means the ocean can take decades or centuries to fully respond to a positive or negative radiative forcing. Why is that bad news for us? If we're in a global climate shift towards warming now, it's going to take centuries, potentially, for the ocean to come full circle and dissipate out all of that carbon that it's been storing in rock called limestone. So, interpreting radiative forcing. A feedback, again, is the Earth's response to radiative forcing, which either increases or decreases the original state. So if you have a positive feedback of the climate, this occurs when the atmosphere stores a higher volume of watts per square meter of energy, causing the Earth's climate to warm. So I know people think positive is good, but positive feedback means it's warming. When you have a negative feedback, it goes back to that chart where we had below 0 and you saw the bars pointing down. They're negative watts per square meter, so this stores a smaller amount of watts per square meter of energy, causing the Earth's climate to cool down. Would the left or the right cause a positive forcing? And you may be laughing at our picture choice here because, the big thing is cows cause methane and they're causing global warming. They're just one aspect of the story. But obviously, if they're ejecting methane, they would be causing a positive forcing. This here would be aerosols causing a negative forcing because you have a lighter colored surface that can produce a reflection of sunlight and energy back to outer space. In this case, it's methane holds so much more heat per molecule than carbon dioxide, which is why we have a positive forcing. So what type of radiative forcing do the red bars represent? They represent positive. The blue bars represent negative on this chart. Very important, you can interpret that. So does CO2 have a positive or negative forcing? Take a look at it. Make sure you know this for test questions. If it's going up and it's above the zero line, it's got to be positive. If aerosols cause a negative or positive forcing, which one is it? Well, the aerosols are blue, they're pointing down, so it would be a negative. So now that we know a little bit about feedbacks, let's kind of apply that to the bigger picture of climate change. When you have a positive feedback, and remember positive means you have a higher kilowatts per squared meter, this will cause a warming effect. Why does that happen? Because it's caused by greenhouse gases. So as we interpret what we've learned about climate feedbacks, let's just kind of redefine what that moment is. Attempt to try to solve this problem for us by sequestering as much of that carbon into rock as possible, specifically in limestone. So what does sequester mean? Absorb it and actually turn it into something. So when this happens, that means we got all this limestone full of this carbon. And as I mentioned earlier in the lecture, there's several ways that that carbon can be released out of limestone. Increased acidity in oceans, and then of course, when we extract limestone as humans and start to use it for things like cement production, we start using it for rock crushing operations, that's going to release that carbon back into the atmosphere. The ocean currently contains, and this is almost a drum roll moment because it's incomprehensible, 50 million gigatons. I am encouraging you to look up what a gigaton is comparison to a normal ton, and I think you're going to be absolutely floored. So essentially, if we were to look at our problems right now, this is the total volume of what we have known in fossil fuel reserves, and this is if our future emissions are greater than this, the climate change will be catastrophic, because we're going to, if we have this much left and we're already in a trouble, that means we're going to be reaching that 100% multiple times. So I'm wanting you to get that that means we're going to be raising global mean temperature by 1 degree Celsius each time. In the next lecture, we'll discuss what does this look like and what actual magic number does it take to get there. So that's a great place to take a break if you feel like, oh my gosh, I need a sanity check. Most people do when it comes to climate change. So I'll see you back in a little bit to watch part 2, our very last lecture of this semester. Climate change. Bye.